Does anyone know what this is? Yeah, well, go ahead.
It was proved that 1 plus 1 was equal to 2?
Yeah, that's correct. In the 20th century, Bertrand Russell conducted a proof that proved 1 plus 1 equals 2. And, well, as I said, it was conducted in the 20th century, and I thought that was quite late. I mean, quite a lot of buildings have been built by then, quite a lot of infrastructure was around, people depended on money being valuable. What if 1 plus 1 wasn't equal to 2? What if they proved it wasn't equal? I mean, the whole world wouldn't know what to do anymore. Money would be worthless. Well, now that I've got your attention, I'm going to talk a little bit more about concurrency. I'm going to prove a concurrent algorithm called LACE, but before I talk about that, I'll explain what concurrency actually means. Well, in a computer you have got multiple processors. Let's say we have 4 like this. They can work on the same data simultaneously. So they can modify the same data. But this brings some problems. Let's say you have a bank with 2 people. They both have 100 euros in there. Alice and Bob. And let's say core 1 and 2 act on this data. Core 1 will read the data and see that Alice has 100 euros in her bank account. Then it will want to add 50 euros to that account. Simultaneously, core 2 also reads Alice's bank account and sees that there's still 100 euros in there. Well, next thing you know, core 1 is going to add the 50 euros and store 150 in her bank account. However, core 2 wants to subtract $50 from her account, but it still thinks Alice has 100 euros in her account. So when it wants to store that, it stores 50 euros in her account. Suddenly she has lost 50 euros, and that's something you don't want, because she should still have 100 euros. Well, these are the problems that may arise with concurrency. Now let's take a look at LACE. That's the algorithm I'm going to prove. It is a concurrent algorithm, and what it does, it takes a workload, so a task that needs to be executed, and it distributes it over multiple cores. So it says to each processor what tasks it has to compute, so the final result will be correct. It uses a D queue, that's a double-ended queue, and for people who don't know what a queue is, it's like a waiting line. And I have an example for this. The double-ended queue can be modified on both the head and the tail of the waiting line. So if we have the queue here, the head can, for example, add a task or add multiple tasks. And then the tail can read them, and the head can also read them. That depends on what you want them to do. So, sorry. So the tail can read, and the head can read or delete, for example, stuff as well. That's what the queue does. Now LACE will put tasks in the queue and will call programs to take tasks out of the queue for them to execute. Well, LACE also uses a couple of concurrent methods. As I said in my title, it is a lockless algorithm. That means, as Swan already explained to you, algorithms using locks give a lock to a certain core, and then they can use that, and then they give the lock back. However, this is quite expensive, and therefore we would like to use lockless algorithms so that don't use these locks. They have different methods, such as compare and swap, for example. What a compare and swap does is, I've abbreviated it here as CAS, CAS. It looks at a certain point in the data. So, for example, at Alice's bank account, it sees that there's 150 euros in there. It expects there to be 100 euros in there, because that's what they've read. And only if these are the same, it will execute the operation. If they are not the same, that means something has changed, and therefore it won't execute the operation. This will make sure that Alice won't be robbed of her money, as in the previous example. Furthermore, it uses a memory fence, and what a memory fence does is when something is stored in the memory, it may not be stored immediately when you want it to be. However, if you use a memory fence, it makes sure that the store that you want it to be globalized will be. So, for example, if a memory fence is placed after this, you know for sure that 150 euros will be stored in the memory. Well, let's continue, because we are going to prove this algorithm, but why? Let's take a look at the probability. In computer programs, something might go wrong, like in everyday, but you want to be sure that it doesn't go wrong. Imagine there's a chance of 1 in 500,000 that there's a small bug in your program. That's the same probability as getting struck by lightning. I mean, it's never going to happen. But if you execute that 100,000 times, the probability will become 1 in 6. And I don't know if any of you have ever played Russian roulette, but I don't think you have, because we don't like a chance of 1 in 6 that something goes wrong. It can also cause a lot of damage, especially if other systems depend on it. As Twan already said, hospitals may use such programs, and if people won't get cured because some faulty software is implemented, you wouldn't be happy. Now let's take a look at how we did this. Here's a little snippet of the algorithm. It's just a small piece. I don't expect you to understand it. I mean, it took me a couple of weeks as well. But in essence, there are multiple processes. One of them is a thieving process, and one of them is the owner process. Now, the thief can, for example, execute its... Well, let me do this like this, because it can execute every line of the program in order. However, because it's a concurrent program, the owner thread can simultaneously execute its instructions. For example, when it comes here, it modifies till to head -1. That's a modification that changes the value of till. Here we see the compare and swap operation that checks whether till is still the old value. Well, now we know it wasn't the old value because the owner has changed it. So if thief executes this line of code, it will fail. However, if the owner doesn't complete this instruction in time, this operation will succeed. So there are a lot of different combinations of different possibilities of combinations for a program to execute, especially when you use multiple cores that do execute this. Well, what we did in our research is iterate over all these different possibilities and check if the program didn't contain any faulty information. Because if there's only one small chance of something going wrong, well, it might as well occur. Well, like I said, in this case, the operation will fail. What this concludes to is that we've come up with a proof, and we've proven that the algorithm works the same as if it was executed sequentially. That means if it was executed by one program that did it in order, instead of multiple cores that work on the same data. And thereby we've proven the algorithm correct. Now, the method for proving this correct was using the linearization points and the order in which they occur, as I explained to you in the previous slide. Since we've gotten a proof, we know that it works. However, it's still an informal proof. We didn't give any automated tool. We didn't use any tool that automatically proved the algorithm. And that was because of the lack of time for this research. Well, what can we still do? Some future work. There should be another slide. Well, I'll tell you something. We can still continue this research, for example, by generating an automatic proof of the program, which will more formally prove the algorithm correct. so that it's even more certain. I mean, I've conducted the proof. I'm also human, so I can make errors or mistakes. And when you automatically do this, we are 100% sure that the algorithm works. Furthermore, we can use this method of proving correctness and implement it in tools such as PVS or Vercore, which is used at the university. So they can also use this method for proving algorithms correct. Well, that was my presentation. Are there any questions?
Where is LACE used? Because I think I saw it in my own research somewhere.
I don't think it's used very widely still, because it's still in development. We've just conducted the proof and we want it to be 100% correct before we let other people use the algorithm. But we can in the future use it for programs when we want to create multi-threaded programs or concurrent programs. There are multiple strategies to implementing that, and LACE is a concurrent work pool strategy. I don't know if you've heard of that in your bachelor program, but this is an implementation for such a concurrent work pool. Yeah. Yes?
Wil je in het Nederlands of do you want it in the English?
English is fine.
Okay, good. Good. I'll do it in the English. So there's always a difference between rationally knowing things and intuitively feeling it. Mm-hmm. So for example, many people feel that homeopathy works. Rationally we know that it's utter bullshit. So you've proven that LACE is correct. Now I wonder, do you also feel that it's correct? Are you confident?
Well, with this proof I already was quite confident. I've read the paper which explained LACE. It was already used on some examples and they produced correct results. So intuitively we found that it was working correctly. But with this proof we're really sure that it works correctly.
Okay.
I hope that answers your question. Any other questions?
If not, yeah, indeed. If not, then I want to thank everybody for their attention and also, of course, speakers.